Alright guys, how's it going? So today we're going to look at the delta sigma converter. We'll look at the basic principles of its operation, and hopefully by the end of this you'll have an appreciation to how amazing this little invention is. So to get started, let's look at a comparator built with an operational amplifier. And you remember the golden rule of op amps? It will always try to make the difference between the voltage on the positive terminal and the voltage on the negative terminal equal to 0. But how? Well, it can only control the voltage on the output. So if we connect the output to the negative input, then we get the feedback system that will always guarantee that the output of the op amp is exactly the same as its input. And this configuration, by the way, is called the follower. Okay, but what if we don't connect the output of the op amp? Well, in that case, then the op amp will max out the output voltage to whatever rails it's connected to. And every time the voltage in the positive terminal is greater than the negative terminal, then the op amp will quickly max out the voltage to a positive rail, and vice versa. If the op amp gets a negative voltage, then it's going to max out the voltage to the negative rail. Okay, so a comparator is also called a 1-bit analog to digital converter, or ADC in short, when we make the voltage at the negative terminal equal to ground or 0 volts. And this is because if we only have 1 bit of information, we can only say that the voltage at the input is either positive or negative. We still need a clock to provide this digitalized information at a constant rate, which we'll call the sampling rate of the delta sigma modulator. So a way to implement this clock is by connecting the output of this op amp to a D flip-flop, which will move the data to the output every time the clock ticks. Cool, so now let's make our prototypical sigma delta modulator by connecting the analog signal we want to sample to this feedback loop. So we have a difference amplifier that subtracts the feedback signal from the input signal. So for example, if the voltage at the analog input is plus 3 volts and the feedback signal is plus 5 volts, then we would have a minus 2 volts output signal. And we now want to run the signal through a low pass filter. And the simplest filter is just a single integrator. But in practice, you might have several integrators in series to kind of tailor the aliasing characteristics of this ADC. And the whole point here is that the integrator time constant will provide a delay that is related to the feedback error. Cool. Now this 1-bit ADC that we developed will close the loop in the delta sigma converter. And this ADC signal is also the output signal, but let's just first kind of admire this feedback loop working, because it's just so satisfying, isn't it? Okay, so now let's have a closer look. So when the voltage of the input signal is 0 volts, then we get a really fast pulse train at the output. Actually, the pulse train frequency is as fast as the clock signal. Let's see why. Well, if we start with the output at plus 5 volts, for example, then we have 0 minus 5 volts or minus 5 volts at the difference amplifier output. Okay, if the integrator was at a positive voltage at its output, this minus 5 volt at the input will make it move really fast, kind of like a step function in an integrator, and go into negative voltage territory. And when the clock ticks, then the output of the ADC will be negative 5 volts, as the voltage of the integrator now is negative. So this means that the difference amplifier will now take the difference 0 minus 5 volts, which is plus 5 volts, and this will excite the integrator in the opposite direction. This will make the voltage at the output of the integrator to go as fast as possible into the positive territory again. And this means that the next clock tick will now flip the ADC again. And now the process just keeps going, and we have this really fast switching frequency, and that's the fastest possible frequency at the ADC output. If the voltage at the input now rises to an intermediary value, let's say for example plus 2 volts, then we can analyze again by assuming that we start plus 5 volts in the ADC output. Then the difference amplifier now gives us 2 minus 5, which is minus 3 volts, which is, and make sure you pay attention here, it's less negative than the previous case, before we had minus 5 volts. So this means that the integrator now will take slightly longer to drop the voltage at its output, perhaps just a couple clock cycles instead of just one. And the voltage at the integrator output eventually goes into the negative territory, and then the ADC output flips again to minus 5 volts. But now, since plus 2 minus 5 volts is actually plus 7 volts, then we get a much faster rise time of the integrator, which will take a single clock cycle to recover, and then the cycle repeats again. So this means that the ADC output spends longer at plus 5 volts than at minus 5 volts, and we can measure this time later by just counting the positive pulses. Cool, so now we're really close because we just need now to count the positive pulses with a counter at the ADC output. And the counter clock frequency is the actual sampling frequency of this system, and it's the rate at which the data is being output at. So this clock frequency is usually a submultiple of the 1-bit ADC's frequency, and the submultiple is usually a power of 2 because we want to kind of make a binary number from this, right? So in this animation here, we're showing actually a 6-bit ADC, which means that every 2 to the 6 or 64 clock cycles, we get a new 6-bit sample from the output. Okay, so this is the basics of this absolutely beautiful machinery that makes the Delta Sigma converter tick. And I hope you found this useful, and please let me know if you have any questions or suggestions in the comments below. Also, if you think this explanation deserves, please hit the like button, and this will probably motivate me to do more of these kind of videos. Alright guys, I'll see you later. Bye bye.